plus, this is the first point, huh? Plus, sorry, this is B. B0 and B1. And here we have a B0 times minus U0 plus U1. And then the next one is factor 1 here, and I have U1, U2 minus U0, and I have a 1/2, right, because this is center derivative, this 1/2 here. Sorry, again I'm putting U, this is V. This is U, and this is V2, U, V0, and here I have plus B1, U2 minus U0, and so on, the other terms. So here you see what happens. You get, there is 1/2 everywhere now, so I can take it out. And then I have a minus U0, V0 from here, and I have another from here, so I have a 2 here. So this is this term and this term. Then I have a plus B1 U0, which is this one, plus B0 U1, which is this one. And from here I will take only the first terms. The others will go okay, because when we did this for the periodic case, all the terms in the middle went away. So that's, we know that is okay. So I just want to take these ones. And so here I have a minus U1 with B0, and here I have a minus B1 with U0. Okay, so this cancels with this with this, and so from the first side of the chain I will get only U0 B0. Okay, so I get this with the right sign, minus. So this calculation gave me this. So this is okay. Okay, so you go like this. At the end, the terms which are remaining, which are the U0 only, UN minus 1, will give you this term with the plus sign. So this works. Can you do it for are there more? One question is, can you find more of these things with only this stencil with 2 points or 3 points? So things which have these two, or in the middle these 3, the center difference and the boundary, and this is unique. This is the only pair. Now we have to talk about not only the finite difference, but the pair, D and H. Okay? This is unique. For the fourth order, is also unique. So when you use in the center, you use all these points, right? The fourth order derivative that we call, this is the second order, there is a unique fourth order. No, I think this is not. This is already not unique. It is this one. It is unique if you require that this to be. You know what happens is that in the boundary, here the error is bigger. The error here, that is the difference between the derivative and the finite difference, the error is delta x. While here the error is delta x squared. You can show that you cannot go, so if you want a method of fourth order, say, you can show that in the boundary it can be at most third order. So there is a unique one if the boundary is third order. And otherwise there are many which are second order in the boundary. And then if you go to higher order, there are many. And there you say, okay, which one of all these I want? And then there are people who have done many different ones, depending on on several criteria. For instance, if you say, okay, say I'm in this boundary, this is the boundary point, I can get a criteria which you say I want to use a less amount of points possible to get to this point. By the way, suppose I want this method, right, which is fourth order. So even here, up to here is okay, but for this point, I also need to do something different, right? Because the fourth order method will require me this point that is not available. So I will have to use something here, some one-sided derivative, even for this point. So for these 2 points, I need to change my scheme for the fourth order. So I change the scheme. And I could say, well, I want a scheme that has the less possible points here with the given accuracy. And that's was the first thing people wanted, some small number of points here. But this is not really important because these are few points, right? Suppose you are taking 100 points, then you have to do a couple of more computations for these 2 points. So that's not really a good criteria numerically of efficiency because there are very few calculations. So other people say, well, I want to get here with the less possible error. So the error will be some constant times, say, delta x to the cube here. And I say, okay, I want to go here with the less possible error. Then I will choose this coefficient so that this constant c is small, right? That I can do. So that's what some people did. And now there is a suit. There are many ways of doing this. Other people have done the following. Say, okay, I have a grid. I lose a pointer here. I have a grid here. And here, further away from the point, I use center it. But near the bound, and these are all dx equally spaced. But in the last point, I will choose here the points in a different way. This distance between the points is different. And then I can get a derivative, a finite difference, which has very good, very small errors, right? So I change the last point. These points are not equispace. So I have a delta x n minus 2 here, delta x n minus 1, and so on. Okay? So I put these points at different distances, and I do the calculation like that. So some people have tried this too, and they have less error. So let me try if we can make implement this in a notebook, okay? So we now go to a notebook. So let's let's try with this notebook. So here we are using this library, summation by parts operators. Remember I used it the other day. If you have not installed, you just put import packages that summation by parts operator. I'm importing also plots, and I will import ordinary differential equation. Okay, so that we can do so here we'll put 11 points just to see what is. And here we have an operator. It was proposed in this paper, Matson Nordstrom, 2004. Derivative order 1, accuracy equal to 4. Okay. Is in between the interval 0, 1. And here we automatically get the grid. We call the grid in this library. We just can call the grid of D, the exponential function, and we can plot both. Huh? So this and now I want to, let's say, I want to take the sine function and we want to plot it. Oh, we just plot u. Here we are going to plot the derivative of u, and here I'm going to plot cosine of x, right? Because the derivative of the sine is the cosine. Let's put 2 pi here so that we here we have here instead of putting plot, let's put scatter, because the points are just oh I only had, here it is. So these are the points of the derivative, and here the numerical calculation is are the points, and this is the true values, right? So here is okay. In the boundary is a bit bad because we are having less definition. Let's put I don't know, 100 points here. And you see that here is already very good. Okay, even at those points. So you can let's go back to 21 so that we to 11. So we can get the coefficients. So here you have a, when you put this, you have all the type of different coefficients you have. So you have a Holoboro, Langsov. For instance, these Holoboro and Langsov are when you want to take derivative of data that is noisy. So this makes some regularization also of the data. And these are different criteria to get, they have not equal space points. For instance, this Matson, the newer Matson ones do not have the equal space point. And there are many which I don't know what they are. Diner, Dorvan, Schnitter, Tiglio, these are the ones. The first one that people start looking at the getting these coefficients, minimizing the error, not the stencil. That is the amount of points. They were the first to say, okay, why we don't do that? And so they created these operators. So you can see the metrics. If you want to see the metrics, you do metrics D, and you have the metric here. So in the middle you will see that is the usual thing, but in the boundaries you have a here is center, but here is off center again, and then the center. So here is center of second order, then you have all this. So this part is different depending on the method, and then things become the usual thing in the middle. Let me take how many points do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a whole metric. So let me see if I can do 2. From 2 to I want to see the middle of the metric from 2 to n minus 2. So I will take out the comma 2. So this is a metric in the middle, but it's too small. That's why I'm not seeing. Okay, let me take, say, 21 points. Let's say 6. I want to see the middle of the metric. Well, doesn't help this. But here you can see some of the coefficients. This coefficient is 1. These are plus minus, and this is another coefficient. Okay? It's hard to see the whole metric because it's a big metric. So let's try to do some, and here you have the dissipative operator too. Right? The dissipative operator for this is summation by parts. These operators are called summation by parts because this property that we were looking, where it was here, this property is called summation by part. When an operator finite difference satisfies this, we say it satisfies summation by parts. So here is summation by parts for derivative dissipation operator of orders 2 on a grid between 0 and 2 pi using 25 nodes, coefficients of all the information. So this we call Kreis-Holliger, okay? So we have the dissipation operator now, and now we can generate some problem, okay? So we have to do the function f, and the function f will take the u, and the function f is just this, right? Just d times u plus k. Then we can create a problem between 0 and 1, say, no parameters, solve, and so let me now, so this is a problem, but before we will create the initial data, let's call f u the initial data, well, the bump function, bump of x function. I'm trying to waiting that the help will produce a function, but it's not. Okay, here is a function. So we'll put some, we'll help this, no, this x initial, x final, and p. let's see if it remembers the function, so I don't have to. Well, I can bring it from these others. Let's bring these things from here. Here we have the bump function to make initial data. Yeah. So we have the bump function. Which x are we taking now? Let's take 100 points. We have this bump function here. We produce this, we put u0 here. The the coefficients you can get the metrics. With the metric operator you see the coefficients. So if you want to get the coefficients here, they are in the library. But if you want to say, for instance, this one we are having here, then you can get a metric like this. Huh? And so let's say let's look at the rows. So we take I think first is the row, right? The row 1. Let's say the row 10. No, I think I have to take the other way around. So it's 10 here. These are the rows. I was looking at the columns. Can never see the whole. Yeah, here are the coefficients. You see, we are in fourth order, so there should be 4 coefficients, and these are the coefficients. This you have to multiply this by the dx. So because this is divided by dx, so I will put grid of d, and I will take the distance, the first point, second point. So the grid starts at 0, so the second point is just dx. So and here you get the coefficients, right? It's the thing that we had before. So in the middle is just the coefficients we know, and in the boundaries, say if you take the first row, you get these 4 coefficients. The second, you get the center operator. The third is again different. I think this might be one of the ones that have a different dx. So let me do like this. Well, I've already put it, so it's x3 minus x2. No, it's different. And then we go to the fourth. This is again different, and the fifth, I think is okay. It's already the, yeah, the fifth is already the center. So you have to go. You have a head in the matrix which is 4 by 4, which is different, and then the rest there is a block which overimposed with the other, where you have all the middle elements, and then there is a block in the end which is different from 0. Okay. So this is symmetric. This library is very good. You can get all the information, and you can go to the source and look at the coefficients. The coefficients are lists which are there. I myself did these ones, these Lanxos, low noise. I create them. I put them in the library. And one of the Holoborok for a project I was doing, where there is a lot of noise. So we have the data. Plot x of sol of 1. And doesn't like it. I don't see the error, so we'll open another scene here and try to compute, for instance, f of du, but at 0. Just compute this. And we put this is equal to 0. This is nothing. F we create the du. Oh, the error that we had the other day. No. But let's. I thought it was the problem that it was making the U0 real. Attempt to ahí está. Ah, no está de... Claro. No, claro, vamos a ponerla bien. There is a problem with the U0. So I'm restarting everything because there must be something. Okay, I think the problem is here is... There must be a problem between the libraries. If I imported all the plots, I was importing another thing that was called grid. Why is he doing all these things? I mean, this was working okay. It's the derivative operator. No, creates the grid. There must be a problem here in the... Okay. Let's start with... there must be a conflict between the grids. Yeah, it's for the... Right. Yeah, but I think there is a conflict with some grid in the plots. Now it's working, huh? So it's a conflict with the grid and the plots. So this works okay. So it was okay. And here we have there. Let's try this in here. He doesn't like the function. Maybe it's a problem with no. Okay, let's take a break, and I will try to repair this. I don't know what is the error is. So let's continue uh, at 11:40. Okay, so I have time to repair this. If not, I have another notebook, so we can do it. So we meet at 11:40. So now I'm going to try to see what's going on here. Ah, okay. There is something wrong here. U0 is a function. Okay. No sé por qué esta... Fíjate, hago el scatter de esto y me da una porquería. Con... Es como si el U0 tiene poquitos puntos. 100, 101. Sí, P es 8.
Pero esos son, también eso de ahí. X, ¿cuánto tiene?
110. Pero me da esta porque, o sea, me da mal esto. El U0, ¿ves?
A ver, mostrame el bump de vuelta, la función del bump.
Tiene que tener algún error el bump.
Sí, porque tiene un if que da ciertas longitudes, 0.4, 0.6, si está en el intervalo 0.4, 0.6 hace algo, si no, no hace nada. El intervalo debe ser muy chiquitito.
No, pero tengo 100 puntos.
Sí, pero vos tenés un intervalo de 100 puntos, pero vos estás entre 0.4 y 0.6.
Sí, tenés 10 puntos por lo menos.
Eh, ¿Cuánto es la longitud X?
No da
A
simétrico.
ver el plot.
Ese es el plot.
No, el scatter. ¿Pero por qué pone tan pocos puntos? Que no entiendo.
Debe ser algo mal en la función.
¿Y cuánto? ¿Esa es la longitud de lucero que me pusiste ahí?
Sí, 110 elementos.
X, ¿me lo puedes mostrar? El vector X, escribí el vector X.
Es una...
Pero
Es...
el límite de X está mal. X está entre 0 y 2 pi, tiene que ir entre 0 y 1.
No, no si estoy haciendo entre 2 pi.
Pero fíjate, al plot lo estás haciendo el límite entre el plot entre 0 y 1 y 0.3, 0.7 y X está entre 0 y 2 pi. Es otra cosa.
Ah, acá.
Ahí, y fíjate el límite del bump, que esté entre medio, que esté entre el pi menos algo, el pi más algo. Ahí lo vas a ver. Eso es lo que estás viendo.
Claro, claro. Bueno, voy a sacar los pi. Porque eso lo hice para la derivada esta. Ahí está. Ahora está funcionando. No está funcionando. ¿Qué le pasa a esto? Okay, let's continue. I got all the things together now to continue. So let me show you. Uh, we had the initial data. There was a problem here in that instead of having u naught was defined as a function. So now I define the function with the name of bump as we had before, and now u0 is a set of numbers, okay, a vector. So and I define the function here. I put some as before. I put some the a, the d as we had yesterday, but I added two more parameters, which is the dx of the simulation and g. And g is going to be a function, the boundary value. So first we just use the same function as before, and we comment this line because we are going to do it later. This is how you put the boundary condition. So we evolve up to t equal to 1 with a equal to 1. We take the dt. Here we define the dx so that we are going to enter in the... We put the boundary condition here, but we are not going to use it at the moment. And then the d that we use here is just d plus Kreisoliger. This is not necessary. Let me put a 0 here. So that we don't use Kreisoliger for the moment. And we put the dx and the g, but in the functions they are comment. And so we solve as before. What happens? I did something wrong. It was working very well. A is 1, T1, dx, c. This is the d. I don't know what is wrong now. The initial data is okay. Let me uncomment this, but I don't think this is a problem. No. Things are not moving, but I don't know why, because I'm doing multiplication here. T is okay, A is okay, dt is okay. This function we are not using. I think the only change I made was taking this here. Okay, with the Crazy Oliver is working. You see here you have the initial data is in blue, center at 0.5, then start moving, goes to the boundary, and goes away. And the t equal to 1 is just this flat line here. So the wave have gone away, and there is nothing in, because I didn't put any boundary condition. So I should put something here. So the method is stable, but just with no boundary condition. So now I'm going to put a boundary condition. The way we are going to put it is as follows. We change the last point. This is the last time derivative of the point on the right. We say is the point we had from this calculation minus, and here we have a, which is velocity of the wave, dx, and here we have the value at the end minus the value we want to put. I'm going to explain this later on, tomorrow, because we will not. Maybe I'll have time now. So this is the way we are going to do. It might be that there is a 2 here. I'm not sure. I'm going to put a 2 to see. We are going to deduce this formula later on. So now I put this line, and here I have as data in the boundary. I'm going to run with a sign, right? So we enter a sign on the right. You can do other things, say for instance wait and then put something, some more sophisticated function. So we run it, and we got some. I think this is the 2. Shouldn't be without the 2. Okay. Yeah, it's without the 2. So we see the wave was going away, the bump, this way, and here it was entering a wave here. You see, this is the end after 1, and here it start the wave entering, and you see it going down and continue. So let me put a different initial data. So we put only boundary data now, so not to get confused. So I'll define here a new b0 equals to 0th of n. So the data now is 0. I put here b0, So we don't have any data at the beginning, initial data, and we see how the wave enters. It enters like this at the beginning, t equal to 0, there is nothing, t equal to 0, 1 is the red one, right? It's entering this wave. You see these lines, these are not, the error here is very big, that's why you see something funny. But it's entering, here is already entered and went to 0, and here is a 1, okay. And here you see it's more or less okay. So I can take a delta t smaller, say 0, 1, much smaller. And here you see the, this should be better. I don't know why we get all this noise here. Let me do it with a higher n. Let's go to 200. Now it's better. There is a wiggling, but it's smaller, okay? And you see how it works. So now, so this is a way, eh? Here it enters the whole sine wave, and you see here, there is a bit of noise here, because this is entering. So we can compare with the plot of x sine of 2 pi x, okay? And you see that they are 1 over the top, and there are some small difference here. This is always bothering me. So like this. So this is a good way of doing the calculations. Of course, you can take higher order operators. Here I was taking Matson. Order 4, I could take order 6, say. And instead of the Runge-Kutta here, let's see, I have to be careful that I had some of the thing I have to run again. This I have to run again. This not. And we can change here the derivative, the time integrator. We can put the tz. I think it's like this. No. This. I don't remember what the name of this thing. No. Let's use this big one that we have, order 8. Euler, Runge-Kutta. Sit pub 8. Okay. We can use this. And you see that you get something very, very precise. No? So this is a way of giving the boundary conditions. So now I have to explain why we are doing this way of putting the boundary condition, this way here, okay? So you see in the last point, you add a term that has a minus here, a, the value here, and minus the data you want to give, okay? So let me show you why this has to be like this, or can be like this, maybe there is. So I want to explain now the penalty method. So what you want to do is, so you have your problem, dt of u equals to a dx of u. So you discretize and look at the semi-discrete problem where we do the analysis, a du, and this say there is a pair now, h du, so that with this, the scalar product of this h, this operator satisfies this summation by parts property, okay? So you might think, okay, the way of putting boundary conditions is not solving this to the last point, but in the last point say, okay, b at the last point, n minus 1, is my g of t. Okay? That might be one way of doing this. But notice that if you do that, you are breaking the summation by part because you are not using the derivative at the last point. Okay? You are just imposing this. So you should take this up to n minus 1 and then up to n minus 2 and then use this prescription. And that was what some people was doing for a while until somebody discovered that this was really unstable. So it's not the right way. So what they devise is the following. You say, okay, I will use all these equations, but now I will impose this boundary condition the following way. I put something here. I will put a minus sign here. Some constant here. And here I will put b minus g. Okay? What is the idea here? That if this constant is big, you have, forget about this, you have in this part of the equation says, okay, if b is bigger than this number is positive, so this is negative, so it brings b down. If b is less than g, this thing is negative, so with this sign I get something positive, so that brings b up. Okay? So this is a penalty. It's something that if you make a mistake here, the equation will try to correct. Alright? So the idea is to put something like this. This constant c has to be big, so that this will drive this problem to the right point. But now we have to look at the stability, because we are changing the way we are doing things, okay? So now we do the energy estimate. We do the sum. Let me write things like that. So this is the sum over Hij of Uij Bj. Okay, so I don't have to do all the summing all the time. So the energy for this is B with B. I take the time derivative. And when I do that, for this part, I know what I get, right? I get A times B n minus 1 square minus B 0 square so for this but for this part I will get this part. Remember this sum is, so this will act only in the last point. So this, if this is a point I, this is I, and this only in the last point. So this is the last point, and there is a delta I n minus 1 here, right? So this acts only in the last point. So from this I will get the B, the H n minus 1, which is this thing, and then I will get 1 B n minus 1 from the multiplication of this side, and there will be a factor 2 here because we are doing on both sides. I mean, it entered twice, right? So there is a 2 here, and then there is a minus C, this one, and here we have B n minus 1 minus G, okay? This is a boundary term. So this, the whole thing is equal to, this we don't care because this is negative, so I will only take, well, let me write it here, minus A B0 square, and then I will have plus A Bn minus 1 square, and from here I have a minus C, I have a 2 here, I have a H, let me write H, not the whole thing, H, and then I have a Bn minus 1 minus G by Bn minus 1, okay? So now I want this C to be, oh, and I forgotten something. This H, I have a dx here, right? So when I have a this H is some numbers divided by times dx. So when I have a dx here, they cancel all, and I'll get this. But this term still have a dx here, so I have a dx. I'm forgetting the dx. So there is a dx here, right? So I want to get C as much as big as I can, but in such a way that this thing is positive here. Okay? So this term is A Bn minus 1 square. So there is a positive term here that is A minus 2CH delta X times Bn minus 1 square, and then I have a term which is plus 2CHG Bn minus 1 delta x. Okay? So when I can when can I guarantee that this is going to be negative? What do I need? You know, this term, so I have something like this. A times x squared plus b times x, okay? So when is this going to be negative? What conditions do I need? Well, suppose first I need, for this has to be negative for all x. So first what I need is these things to be negative. So a has to be negative. So I will write this as a minus here, and I will use a positive. And this part, right, should be, this part here is less or equal to, let's put a 2 here for doing this. This 2 is less or equal than b squared plus x squared, okay? B is something that doesn't depend on x, so it's okay, I can have any sign. But I want the things that depends on x to be negative. So this thing here is minus a, but I don't remember very well this calculation. I can put an epsilon here and here, so I got an epsilon here, square, and an epsilon here, square. So I get minus a x squared plus epsilon square x squared plus b squared over epsilon squared, okay? So this is bounded by this thing. This I want smaller. This I want to be, yeah, this sign. So I want this to be smaller than 0. So for these two terms. So notice that epsilon I can take any as small as I want. This only depends on g, doesn't depend on epsilon. So this is something that depends on the initial data. And so what I need, and in the end, is that this term here is negative, okay? So I can take the constant c to be what? Has to be bigger than, c has to be bigger than, or in the case with I have 0, it will be c is h over 2h delta x, okay? So if I take c bigger or equal than this, I guarantee that this thing is going to be negative, and so I will get stability. And so I have to consider these constants, okay? Bigger than this. And in the case we were when the derivative operator is the second order one, the h corresponding to this is 1/2. So this will give me 1. So in this case, a over delta x is okay. That works okay. For the D4, I need to compute this h, right? There will be an h4 in the last point, and so I have to put it here. So my C I just construct this way. Get the delta x and the h, right? And for this h, there is something here. When you compute in this library, there is a way of getting the scalar product, but I don't remember. I have to look up in the library. I don't remember the name. No. No, I don't remember. It is in the library, so in the documentation of the library you can find it. But so you can get here in the function f that we have here. Here I have a over dx. You can define h equal to something that depends on d, and use here divided by h, okay? Divided by h and divided by 2. Because this 2 is the one that we had here. So you have 2h, okay, dx. So you can automate this. It will take any derivative operator and it will give you the correct coefficient, okay? So that's how we impose boundary conditions. So in this calculation here, when we take the C bigger than this, then all this part is negative, and the only thing that it remains is this part here. So what you get is a dt, the epsilon dt is less than or equal to b squared over epsilon squared, and the b has a g, right? The b was all this part plus a dx, right? So it's less or equal to 2ch delta x is just a, right? This is just a, so let me put a here. A square g square, okay? So this is the term that you get, which is basically what you want. At the boundary, you want to bound the energy with something like this, okay? In the continuum, you get this, the way we did it was with an epsilon equal to 1 here, and you get the g squared. So you get the same estimate as the continuum. And this method is very stable, very strong, so you don't break it very easily. The only thing is that suppose you have a system now. Suppose you have a system. dt of u equals to a I d I of u plus something. So you will get dt of b equals to I d I of u, of b, sorry. And then you have to look at this matrix in the boundary. So in the simplest case, and it's a case where you can do all the calculations, you have a boundary. Let me draw it. It doesn't need to be like this. So you have a boundary, and you have coordinates here, so that this boundary is some coordinate, say y equals to constant, to let's put y0 here. So your boundary is some of your coordinates 0. So this here is the component, the boundary matrix is the component y. And so what you have to do is to find which are the eigenvalues which are positive or negative for this matrix. And for the negative, so you have to diagonalize the metric with this matrix. So you have some of your variables. There will be dt of b1 up to s, where your scheme will be just this one. And these are where this matrix is diagonal, right? The boundary matrix diagonal. And here you will put nothing. And for the other ones, the one you have to give boundary conditions, s to the n, if there are m variables. Then here you do this. You put this in here, and you add here you have to use the eigenvalue correspond to this, say s, over h2 delta x, okay, times b twiddle minus the values you wanted to give. And here in this g, you can put these other things, right? There is no problem. So this is a way you put the boundary conditions. This is not trivial to do, because in general you are not in the eigenvalues in the basis where these are the eigenvectors of this matrix. So in the boundary you have to go to the eigenvalues, the basis, do this calculation, and maybe at the end you return. So there is a base transformation here. You go to this base, do this calculation, and then go back, okay? So for instance, if you have a base, the b, and the other base is q minus 1 b Q. Then now you say, okay, I go to this base, I build this, and then I take this equation and multiply by Q and from the left and minus Q from the right, and I get something which is something like this. Let me call alpha this index. This is the same because the transformation doesn't do anything here. You go back to the same thing. And here you get something which has been transformed. Q, this, Q minus 1, right? So you have to write down what this thing is and then put it back. So in a system, in a big system, it's a mess. It's not easy. But you can do it. You can do. We have a codes where we have done for the wave equation, for instance, for the Maxwell. For Maxwell, for free. Many systems. MHD is done somewhere, etc. So you can do that and treat these boundaries. But the boundary have to have this property that your points are aligned with the boundary. So you have these points are in the boundary, okay? So for instance, if you have a square grid and you want to take something like that, which is not aligned with the grid like this, then you have to use some other methods. You can do this, but it's quite tricky. So you have to interpolate here and do many other things. So in general, we prefer to get a grid that is aligned. So you change the coordinates so that this grid is aligned. And that's not easy to do all the times, but for instance, we have a code where we have for instance, a code that you want to take a hole here. You can do two grids, one grid that goes like this, and another one that goes like that. And so the boundary of and this goes like that, and this goes like this. So there are two grids here. This one, and there is another grid here. And so you can solve here with this boundary is okay, and this boundary is okay. And you can solve here, and these boundaries are okay, right? And the way you do it, you just pass information in this grid. These grids are touching here, so there is points in this grid and points in this grid, and they are aligned, so you can pass information. They are at the same physical point. So I'll show you then how to do this. So you can glue grids together and make, for instance, evolution here. We also do evolution we can take, for instance, some grids like this. How many I need? We can get 4 grids like this, another grid like that, and another grid like this. Glue this to this, this to this, this to this with this one, with this one with this one with this, and you see there is no boundary here, so what you get is a sphere with these grids. Okay, so you can get a sphere with grids, and then you can put you can give volume to this. So for instance, you write a grid now on top of this like this, and here like that, and here like this, right? So what you're doing is having the region between two spheres. Okay, so you have a region to integrate which is between two spheres. And this we use, for instance, if we want to study, sometimes we have a black hole or a neutron star, and you want to study what is going on here, we do use these regions, integration regions like this. Okay? And this is how do we pass information here? Well, we interpret this as a boundary. So there is a boundary, so at this point what you have is one grid here with these points, and continue here, and on the other side you have another grid, and you have these points. These points are in the same physical space and this. I put separate so that you can visualize, but they are together at the same point. And so the idea is, you say, okay, how I do pass information from this side to this side? Well, if you have a wave, imagine in the continuums, you have this boundary here, and you have a wave like this. So this wave, you say, okay, this wave is going out, and when it reaches here, I put it as a boundary condition for this wave here, so that the wave continues. If I have a wave like this, then when it reaches here, I will pass it to the other side like this. Okay? And the metrics here, when I do the calculation, the I, A, and I, is the same for both sides, because with a different sign, because this surface is the same for both. So this metric is the same, but here I have the normal of the green going out and the normal of the red going out like this. So there is a change in the sign. And this is okay, because then the wave that is going out here has a negative sign here, a positive sign from this side, but it has a negative sign for this side. So I have to give it to continue. You put boundary conditions. Sorry, this side is negative, so I don't have to do anything. But in this side is positive, so I have to give boundary conditions, so I give boundary condition. The way that is going out here has a negative eigenvalue. When it crosses here, it becomes a positive one. I'm doing it wrong. this side, this way have a negative one. And when it comes to this side, I have to give boundary conditions to the positive ones. So this is negative, I don't have to give anything. I'm confused with this thing. This changes sign, so when something is going out here, from this side is negative, so I don't have to do anything. But when I move to the other side, this is positive, so I have to give something, okay? And so that's how it works. So to pass information in this region, suppose you have a wave that is going like this, it just passes. And then here I let it go. But here it just passes. Huh? And if I have a wave coming like this, it goes like this. Okay? So that's how it works. So you can do all these things with the same infrastructure that we are having here. So the only thing you need is to use this penalty method, not only in the real boundaries, but across boundaries between different grids. So you have a grid here, a grid here. To pass information, you use the same grid, the same penalty method from one grid to the other. Okay? So this is all what we need to do and what there is for boundary value problems for finite differences. So next week we are going to discuss. You have the other lab to give it back, I think, in Monday morning. So next week we are going to make lab 4 in the new notation. And in this lab we are going to do boundary value problems. Okay, so we are going to apply this. So I will finish this notebook I was doing. This notebook I will write it, okay, and I post it so you can use it. But in this lab, you will have to create these D operators. You will have the D2 and you will have to create the D4 by hand, so that you learn how to do it. Check the energy, do calculations and compute the Q, of course, right, to see that you are okay. Okay? Questions? Virginia, she asks, will it always be the same metric? Does that depends on how you design the problem? You mean the metric, this H in the you mean the H? This HIJ? Yeah, the H depends on the D, so they come together. So every D has an H. The H for the D2 was something. The H for the D4 that we are going to use is something. You will see how it is. But depends on that. And it doesn't matter if the grid is like this or whatever, as long as the dx are the same for all time, everything in the same direction are the same, then this the h and the d's are okay, are the same. So you can use anything you want. So that's why in the library comes there is a function that I don't remember that says, okay, scalar product, that is this h of the d, and that's what you have to use. And it's the last point or the first point, whatever, if you are at the beginning or the end. And they are symmetric, so the last point value is the same as the first point. Sometimes there are some cases where this h is not diagonal, right? For the d2 and the d4 that we are using, the h is diagonal. So it's a diagonal matrix, which in this case has a 1/2 here, ones, and 1/2 at the end, and zeros. But there are other cases where the h is not diagonal. The h is something like different from 0 here, diagonal here, and then different from 0 here. Okay? For instance, for the d4, R1 that is diagonal, and in the boundary is only second order, becomes second order, and there is a d4 which is non-diagonal, and the d here is third order in the boundary. And there are many other things. But fortunately, people have already computed all these things and done all the theory, so you have to use it. The important thing is to know what it is and how to use it. Any other question? Thank you. Okay, we finished for today and for the week.